I'm Zhuang from Kernel Group. I will talk about the Polygon and Polyhedra.
My name is Jaebum, and I'm gonna talking about the polygons in first half, and rest of time, the Jan here will talk about polyhedra. So it seems like most of our attendees already listen about the polygon during Charles' talk, and I'm gonna just go a little deeper about it. So this is outline of talk. I'm gonna do talking about some representation of polygon and some new constructors and some of new functions around the polygon. So first, here's the very basic, the polygon description, like what we used to use, 3 point. And then here's another one. It's eventually same polygon, but just order of coordinate different. So this is like a clockwise, counterclockwise. So far, so good. But here's another example Charles already showed you. This is the kind technically say self-intersecting polygon, right? It described by 5 points, but it have self-intersection at here. It's easy to see those behavior when you graphically see it, but if you only have this input, it's hard to tell the polygon you have actually self-intersect or have hole or whatever. And internally, we do check those kind of things, depends on computation, but in user side of view, there is no simple way to see if your polygon is good or bad. So we come up with the canonical representation to clean out those kind of issues. So it is simple standard representation of polygons. So it's kind of canonical for polygons, and it helps to implement some low-level computations. So let's see how that works. So we have function called canonical polygon. This is kind of converter that your polygon into canonical representation. So here's the first example. These 2 polygons is the first polygons that I showed you with just different order. And we apply canonical polygons. So it just looks same. And if you actually see what's inside, so this first argument is coordinate. I think Charles already showed you. It's like little version of graphics complex. And the second argument is index. 132, 132 is counterclockwise oriented. And you see these 2 are now is exactly same. So we kind of do the canonicalize. So even you have different description, when you canonicalize, we actually got the actual canonical polygon. And this coordinate we internally sorted using the sort function, not exactly using sort function, but kind of same behavior what sort does. And here's another example, right? And this is multi-polygon. If you just see the graphic of it, you see there are overlapping points between these 2 polygons. And some function in Mathematica, we kind of merging it, some function does. So it's kind of a little bit unclear, and there are some little ambiguity how to treat these multi-polygons. But if you do use canonical polygon, we kind of interpret that geometrically. So we merging these 2 polygons, so we remove the overlapping part. So now it's just 1 polygon with 1 boundary. And here's another example, the self-intersecting polygon. So if you canonicalize, so let's check the input form. So now we have point, the original input, we have 5 points. So after you canonicalized, now you have more point. Actually, this point is the intersecting point. And then here, Charles show you this new description. This is actually polygon with holes. So this outer and hole describe this inside part. And then now you got older intersecting point. So this end result is not the self-intersecting polygon anymore. So it's much more clear. And so this is like about hole. So that description, the way to describe holed polygon is like outer, you specify outer polygon, and holes. The reason I say holes, you can have more than one holes. So it's the list of polygons, which define the several holes. So for example, this one, this is outer, and then it has only one hole inside. And if you see, you got the polygonist holes. And besides that, we have implemented a couple of utility functions to help extract some information of polygons. One of them is polygon coordinate. It's pretty simple. It's just giving you all the point, kind of corner point of polygon they used in, and this is actually the first part of your canonical polygon. And then outer polygon, inner polygon, this is good for when your polygon has holes. Outer polygon always gives the outer boundary, and inner polygon giving you the hole. So if you have multiple hole, it's giving multi-polygon. And if your polygon doesn't have a hole, like a simple polygon, then this will return empty region. So using this function, you can exactly check if your polygon has holes or not, or just extract outer boundary, which is not trivial. And beside the canonical, the representation, we implement the constructors that construct some polygon. So we have crossing polygon, winding polygon, and random polygon. This is 3 new constructors. And first, the crossing polygon. This is basically just using the number of intersecting, how many times that point from ray intersect with the boundary. So for example, like here, inside of this region, the point will intersect 1, 2 boundary. And here, only intersect 1 boundary. We're just taking the smallest number. So whenever it intersects odd number, then we treat it the point is inside the polygon. If it's even, then we think it's outside. So this is example of those polygons. And this is kind of similar to what you do for the basic polygon when it's the single polygon inside of it. And other constructor, people that just see some examples. So this is just, plain polygon which is same to polygon. And here's another single polygon, right? But this is like a multi-polygon, so it has 2 contours kind of intersecting each other. But this case, it behaves a little bit slightly different from the simple regular polygon. So you see here. I will compare the result later. And another constructor we have is winding polygon. So instead of counting intersection between the boundary, this one counting how many times lap around the point using the given the segment or contour. So for example, here in the middle point, there are 2 contours that's surrounding it, and here is just 1, here 2, and here it kind of canceled out. Why? That's why it says 0. And here just -1 clockwise. So at default, whenever it's 0, then we regarding the point is not in the polygon. And when it's not equal to 0, then we think it's inside the polygon. And we have some specification you can specify in this constructor, like even order or three rules, something like that. And whenever the number of winding is greater than 3, we regarding it's inside the polygon. If less than 3, then no. So for example, here, this is all same, the 3 point, right? And this one, you see slightly different behavior compared to crossing polygon. Now you have like filled star-shaped polygon. And if this one also giving different result compared to crossing polygon. So here, I just compare three. This simple case are all three polygon constructs are giving the same result. And single, I already told you, crossing polygon kind of using the same scheme, the regular polygon, and this is a winding polygon. But when you have like a multi-polygon, they intersect each other, you see all three are different behavior. So this one, you do kind of compute crossing polygon for each individual and just union, merging it. And this one, you compute the crossing number separately for each side using the whole entire multi-contour. This one just, yeah, same thing. Okay, and then other constructor we have is random polygon, finally. So this function is very useful when you want to have some example to test the function you implement and see, benchmark. So here's how you specify. We have three different type of random polygon right now. We will keep adding more. But convex is giving you convex polygon. Simple give you simple polygon, so it doesn't need to be convex always. And star shaped is some polygon which looks like star shape, but kind of some property, star shape property, I would say. So for example, like random polygon, it's just giving simple polygon between, I think, vertex size 5 to 15. And here you got the convex polygon. Comma 3 means I want 3 samples. And here's random polygon. Oh, simple, which doesn't need to be convex always. And then star shaped, you see there's kind of, yeah, you can imagine star. And then we have some predicate functions to check what kind of polygon you have. So simple, convex polygon cube. You just see if it's convex. Convex means, as you all know, is whenever you pick up 2 points inside polygon, the line that connecting those 2 points always entirely lies in polygon. So that's just usual definition. And if you take up convex random polygon, that yeah, is true. And then simple polygon, this is polygon without self-intersecting and then also without hole. And certain cases you need it. And this is not simple, right? It's a hole. And last one that I introduced is polygon decomposition. This is basically just decompose your polygon into some more simpler set of polygons. So we have 3 different types. Simple, so you just want to have simple pieces. And then convex, you decompose polygon into convex polygons. And triangle, obviously it's triangle. So it's based on what you need. You can just specify what you want. So for example, I just got some polygon which is not convex, but it's simple. So for example, for simple polygon, you see just one because it's already simple. But if you say, I want to decompose into convex, then you have this. There are certain pieces like this one is not triangle. For triangle, yeah, every piece will be just triangle. So this is about some new feature we added in Polygon. We will keep adding more utility functions and keep improving the things around the polygon. So just keep looking at it. So next, Jan will giving talk about Polyhedra.
Hello? Yeah, so I'm Zhuang. Jaebum just talked about the polygon with dimension 2. I will talk about the polyhedra with dimension 3. Polyhedra is a new graphic primitive. It's now supported in Wolfram language 12. In the future, we plan to work on polytopes with high dimension more than 3. So what is the motivation we want to implement polyhedral. So here I create a mesh boundary region, use the region difference for the two cuboid. Actually, this is a cuboid, and there is a hole inside. So we want to get the mesh cells for the different dimension. So here, the two, we get the bunch of the polygons. So how about the dimension 3? What do we expect? We expect a bunch of the polyhedral. But however, here we get the error message, say no simple cell representation for dimension 3. This is why we need the polyhedral. So for today's my talk, I will talk about the polyhedral and the representation, constructors, operations, decompositions, and so on. So for the polyhedral, what is the input? We can import a bunch of the faces, or a bunch of the out faces. This is the inner faces, or it's the collection of the polyhedral, or we can import the coordinates and the indices depending on the faces. This is like a polyhedral with the voids if we import like the inner faces. So here I just give the small examples. I import the vertices and also the faces. Then we will just get this is the new typesetting for the polygon and the polyhedral. From the new typesetting, it's very easy. We can get the number of points and number of the faces, and click this one, we get more information. So the way we defined the polyhedral is very similar to the graph complex. So the graph complex also we coordinates and faces for the polygons. Okay, in the 12, we also added some platonic solids. For these three is the new graphic primitives. We add of them. Okay, now let's look at the visualization. So here I give an example like from the uniform polyhedral. Later I will talk more in the constructors. So we can use the region and use the options like proxim. Here I use the webs, and we can see the nice the image here. You can operate, you can rotate it. So similar to the polygon, for the polyhedral, we also have the canonicalized form. After canonicalized, we get the outer boundary and the inner boundary. So why we need the canonicalized form? So give an arbitrary polyhedral. If we want to compute the volume, it's very difficult. But after canonicalized, so the volume will be very easy. So just the total of the volume of the outer boundary minus the total volume of the inner boundaries. So this is why we need the canonicalized form. So this is similar to the polygon. We have the related functions can get the coordinates and get the out boundaries and the inner boundaries. Because this is no voids, so it's the empty region. So for the constructor, we will talk about the uniform polyhedral and the random polyhedral. So for the similar to the polygon, we will have the closing polyhedral, winding polyhedral. But we here, these two, we are working very hard on it. It will come in soon. Now we look at the uniform polyhedral. So for this one, we have an intern on Kellen. She's working on it very hard, reading the books, search the websites, and outside software. It seems not so easy. We can get the data from the other software. So a lot of we just manually build it. So what is the uniform? Uniform is mean the each the length of the edge should be 1, and the center will be the origin. So what's the import? We can import the standard name. We collect about more than 17 fives in the 12. Also for the Platonic one, we can import according to the Schwarzschild symbol NM. The N is the one phase, is how many points here. And the M is the how many adjacent faces around this point. So it's 3. So here I just list some nice one. Now is the constructor, the random polyhedral. The random polyhedral we build it from the Covax Hall. So we show some of them. For the other specification, like the polygon, we have the simple one and the Covax one. I think we are still working on it. It will come in soon, the other specification. This is the decomposition. The possible the decomposition for the polyhedral, we have the simple, convex, and tetrahedral. Here I give examples. The cuboids, and after decomposition, we get a bunch of the tetrahedral. Here I just combine them, show that. Okay, so now we will talk about the operations we are supported. We will talk about the dual operations, truncated operations, augmented operations, and so on. These new operations will provide us more flexibility when we're building working on the 3D objects. So first, let's see what is the dual operations. Dual operations is mean give an polyhedral. Then for each faces, it has a center. For each center will be a point in the dual one. And for each point here, there is the adjacent faces will be 3 of them. This is why there is a face here, the 3 points here. So the dual polyhedral, it works for the symbolic one. It works for the general one. So here I created a polyhedral. It's a plane. So we the dual polyhedral for the plane. So what we get? So here we get nice dual planes. So here is another operation, truncated one. Truncated one is mean the cutting each vertices by a less ratio L. So here I just show the different L, and we can see truncated more and more. This is another the operation, augmented one. Augmented one is for each faces we were replaced by a pyramid with a high edge. So here I just show some examples. We get the data from the operation data. If the family is the Archimedean family, so we can see there is a bunch of nice images. We get it. Okay, here is the snap polyhedral. Snap polyhedral is the for each faces, for the points here, we will get the one faces here. And for each edges, we're replaced by a pair of triangles. So here I run some examples, 3 of them, and show the snap. Here is the last one, the beavered operation. The beavered operation is we beavered some edges of the length of the ratio. So also here I show some examples here for the Panasonic one. So since polyhedral is a region, so it works for all the measures, all the solvers. So here I just want to introduce a new measure. It's the polyhedral genus. Polyhedral genus actually is it's how many holes in a polyhedral. So let's look at this cup. So we will see how many holes there. Someone say, okay, it's 1. Someone say, okay, how about this one? Maybe 2. So actually, topologically, the cup actually is similar. It's the same as the donuts. So this is mean the genus should be 1. So here I just show on the from 0 to 3. So here I will give an examples. Yes, 3 of them. So for more information, just go to our guide page. So any questions? Thanks.